Okay, coming to the cusp, before going to the cusp, we should know the basic concept. What is tangent? Tangent is a line which just touches the curve without crossing it. That is called tangent. Means if you draw tangent at the curve, it doesn't mean that it differentiable at that point. Keep in mind. Whenever if you draw tangent at that point, it is not meaning of that it is will going to that point is function is differentiable just as a straight line which is going to why I will tell you in the coming classes how in the coming things I will tell you how this tangent you can say that in this video only I will tell you. Okay, it's just a line which touches the curve at a point. Okay, if suppose there is a smooth curve, means if the function is differentiable at that particular point, if you take any particular point, if I say it is differentiable, doesn't mean that it can, if I draw tangent at that particular point, if I say it is differentiable, not like that. The only thing is if it is differentiable, when it is possible, whenever. Derivative means what? We are going to find out the rate of change of output per unit change in input at that particular point you are calculating. Suppose somewhat C is there, C is the point, C comma f of C we are going to, there is a point here. I want to go, then I want to find out what is the rate of change of curve at that particular point. What we can do that, the both the, I can say that suppose somewhere here some point C is there, I want to find out the rate of change. You choose 2 points, that is left C plus H first. What is the change in the out as H tends to 0? I can say that you choose 2 points, that is C comma f of C and C plus H comma f of C plus H. 2 points C comma f of C and C plus H comma f of C plus H. And right side I'm telling that if you work out the ratio of f of C plus H minus f of C divided by C plus H minus E, that is H, as H tends to 0, we can get rate at that particular point, that is called, if it is equal to the right hand derivative and left hand derivative, because we should get, why, because we should get unique. If you get two values per unit change in the input, if you get two values, which should I can consider, there should be one. Okay, but whenever if you draw tangent at that smooth curve, what happens in this case, the I can say that the left hand derivative and right hand derivative equal. In that case they almost align with whatever the, if you choose suppose x1 y1 is there, left side x2 y2, right side x3 y3, whatever the rate, if you right hand derivative means that is work out y3 minus uh, y1 divided by x3 minus x1, as x tends to x3 tends to x1, if you work out that you can get right hand derivative, which should be equal to the left hand derivative, that is y2 minus y1 divided by x2 minus the ratio, can say that, then it is called differentiable. In that case, whatever the slope of this, the second line, right side and left side, they almost, that slope will give the derivative at that point. Okay, try to understand. We're going to give those slopes, I can say that the second line as whatever the point nearer to that, if you go on near to this point, they align with the tangent drawn at that point. I can say that this align it with the tangent drawn at that point. Therefore, the slope of this tangent will give the slope of the derivative of the curve at that point. Okay, here the condition for differentiability is that left hand derivative and right hand derivative should be equal and the limit should be adjusted. Otherwise, if does not, this not value is undefined, I will tell you here. See here, in case of cusp, what happens? In case of cusp, see here, this is called common tangent, and this is, there are two tangents here for single cusp. One is horizontal tangent and vertical tangent. But in case of this thing, what happens whenever, definitely if you choose adjacent points, this is x1 y1, and this is right side we have x3 y3, and left side we have x2 y2. Whatever the change in, if you work out y2 minus y1 divided by x2 minus x1, if you work, it should be equal. Definitely they are equal, but the limit does not exist. It becomes almost whatever this second line align with the vertical tangent here, the tan of this becomes infinite, because this is right side positive infinity and negative infinity. Almost even though they are equal, but they are become undefined. Therefore you can say that the tan is the function, the I can say that curve is not differentiable at this cusp point, we can say that. One more thing we observe here, whatever this, I can say that even in case of cusp, we cannot say that, we can say the slope of the curve point at a point, I can say that our slope means what, that is what rate of change of output per unit change in the input, that is our derivative at a point. Is it equal to the slope of the common tangent? But equal, almost equal, but it is undefined, keep in mind, because the common tangent is vertical here. And one more thing, if you come into the horizontal, it will never equal, because horizontal, because the slope somewhat it makes an angle of almost, we cannot say that it is not at all it is equal to the slope of horizontal. Okay, that is why with the x-axis. This is how we can. In the case of smooth curve, what happens, the whatever the slope, because definitely want to find out the derivative at point means you have to find out the uh, what is the change in the output, what is the change in the per unit small input at the left side and right should it be equal. That's why we are going to work out the slope of the second line and left side and right side, but it is interestingly it is aligned with the tangent drawn at that point, therefore it is a derivative at that. Only it is in case of smooth curve, keep in mind. But in case of cusp, it is not possible. Okay, I will tell you. Okay, this thing, so as I told you, the in case of cusp, what happens, they are going to meet the point. This is called common tangent, they will going to point at the meet. But is it horizontal, is a tangent, but tangent, because but is not differentiable. Okay, see what happens, there may be a two tangents, because this line will going to touch this curve at this point, and this also, there are two tangents we can uh, okay, mm, draw, I can say that more tangents. But question is, whenever the slope of the tangent is not equal to the slope of the curve at a point here, what happens if you want to calculate the rate we can work out here, that should be equal to the this one, almost aligned with the vertical line. They mean very close to the vertical line. From the right side it may sum of tan of 89 degree, something like that, it is positive infinity. Here tan of sum of 90 plus 0 0 is to minus infinity. The left hand derivative and right hand derivative, they are not equal. Then which change I should take in order to find out the derivative, therefore is not differentiable. Okay, you can take another type of cusp here. See, suppose here also it is not smooth curve. Keep in mind, somewhat it is not smooth. This changes the curve, changes its direction suddenly, but it is not aligned with the. I can say that at 0 0. Can you say that it is differentiable at 0 0? No, it is not differentiable. If you work out, it becomes f dash of x is equal to 4 by 3 into x raised to what happens, minus 1 by 3 means 4 by 3 divided by x raised to 1 by 3. As x it becomes 0, it becomes infinite, therefore it is not differentiable. And this, not only it is a common tangent, it is concave to the this one here, concave to the um, tangent line here. This is also one more cusp here. If you come into the corner point, what happens in this case? Suppose y is equal to mod of x is the function of the curve, No doubt you can draw tangent, but at this point there are infinite. This is horizontal tangent and vertical tangent to this curve. This, but here the slope, if you work out, I want to find out the derivative at this point. What happens actually? Derivative does not exist at this corner point. Why the question comes here? We have to calculate the derivative. As I told you, what we can do, we have to work out the per unit change. Means as we bring the point x2 y2 right side are very close to the 0 comma 0 here, what happens to the, if you work out the ratio of that, it should be what, and left side and right side should be equal, then only you can say that this is the change in the output per unit in the change in the input. But if you come into the left hand limit, as it tends to 0 from the left side, what happens, the ratio of, we can say that f of 0 plus h minus, sorry, left side you can get f of 0 minus h, f of 0 minus h minus f of 0 divided by h is negative here, that becomes, I can say that here h divided by my h minus 1 you can get, because h is negative here. Whenever mod of x is equal to x is less than 0, we can get minus x, therefore we can get minus 1 here, right? That is from, I can say that left side we have minus 1, but right side we have 1. Means the left side and right side does not exist, therefore can left hand derivative and right hand derivative, they are not equal, therefore this is a corner point, you can say that, because they give left side we have somewhat that, we can say the rate, per unit change in the different output, you can get it like that. Coming to the different types of cusp, single cusp with first species, what happens in this case? Suppose this is a cusp here, as I told you, as they are very convex to this common tangent here, and this is also no doubt tangent, this is perpendicular to the this given tangent, normal we can say that. What happens, both branches are on the opposite side of the tangent, but one side of the normal, see here, one side of the normal and opposite sides of the tangent, this is called a single cusp of the first species. Okay, the second one is single cusp of the second species, means the curve stays on one side of the normal and one side of the tangent, that is called, see here, this also point is, we cannot say differentiable, because we have 2 points here, 2 points, but the curve comes like this and goes like this. Okay, there, there I can say that if you work out these things, um the left side, what happens, the left side is this one, somewhat slighter angle with this, you can get finite value, but right hand left hand limit and right hand limit, they are not equal here, therefore you can say that the whatever the, if you choose the point x2 y2 in this lower branch and right, and x, sorry, if you choose x3 y3 on the lower branch, if you choose x2 y2 on the upper branch, what this point, let us assume that this is x1 y1, if you work out y2 minus y1 divided by x2 minus x1 ratio, that is given by the slope of the second line joining the, I can say that x2 y2 x with x1 y1, which makes a slighter angle with the positive direction of, because the tangent is along the x-axis, positive direction of the x-axis, and slightly up the upper branch makes an angle for thus whatever the second line, if you choose it, joining the x3 y3 and x1 y1, which is somewhat a tan of some higher degree than this lower branch, therefore I can say that they are not lower, left hand limit and right hand limit, they are not equal, this is called second species. Okay, single cusp of second species. Next is double cusp. Suppose we have a double cusp with the first species, means branches on both the sides of the normal. What happens? The branches are there, no, both the sides of the normal. Means this is cusp 1 and this is cusp 2. See here, this is cusp 1 and this is cusp 2 here. And the branches on opposite sides of the normal tangent, so opposite sides of the tangent, but not single sides on same sides of tangent. Opposite sides of the uh, tangent is there. This is called double cusp of species. Then, as I told you, double cusp of the second species means we have, when you have already single cusp of, if you leave this part, okay, say if you leave this part, you can get what you can get. This is single cusp of the second species means all the branches of the cu- cusp are on the same side of the tangent. But here this one somewhat the branches of the cusp are, I can say that, we can on the lie on the opposite sides of the normal, okay, but only one side of the tangent here. This figure you can say that in this point also the the function is not different. So they are the different types of the cusp. I can say that double cusp, but only it is, if you remove this part, you can get only that is looks like a single cusp of the second species. And if you just symmetrical about this, I can say that normal. Okay, this is how we can understand the things. The key understanding if is that if the tangent may exist but differentiable or not, it depends upon these three things: whether the left hand limit or right and equal or not, then limit exist or not. If it is exist, it is finite. It should be exist means it is finite only. I can say that it is, should be a finite. And left hand derivative, the tangent may exist. It doesn't mean that differentiable. Try to understand. Whenever if it is differentiable, definitely the slope of tangent is equal to the, I can say that the slope of the second line adjacent to the on both the sides. Okay, this is how the slope of the curve at a point. Okay, this is how we can understand the things. Thank you. And the same thing as that if the limit must exist, limit must be same from the both sides. This is how can the different types of curves we studied on those things. Because one more thing, what we studied at the corner point, we cannot say the function is not differentiable. And why then I can say that why suppose, even though we can one more thing, if you I forgotten to mention here, why one may ask that if you suppose you take a point of x1, x2, y2 and x3, whatever the second line makes almost, I can say that tan of 0.00 degree, that is 0. But if you work out the x3, y3, this point from line, second line joining this point becomes minus. Even though the left hand derivative and right hand derivative exist here, but they are not same. They somehow point minus 0.00 something here. You can get positive 0.00 opposite side. You can get like that. Therefore, you cannot say that it is not differentiable at this cusp. Keep in mind, this is very important.